It spins. The jet doesn't. Two motions, one refusing the other, and that contradiction is where everything begins. There are celestial behaviors we believe we understand, not because we've seen everything, but because thousands of observations have carved familiar patterns into our expectations. A comet spins, and its outgassing follows. A vent erupts, and the spray curls in response to rotation. Angular momentum imprints itself the way wind imprints across grass. Automatically, inevitably. But then, 3I, Atlas arrived, and something stopped obeying. This object is rotating, not ambiguously, not debatably. Its 16.16-hour period is one of the clearest features extracted from the light curve. You can see the brightness rise and fall with a dependable rhythm. You can plot it, you can model it, you can predict it. And yet the jet, this long, thin, unwavering structure, refuses to acknowledge that rotation at all. It stays still, not almost still, not approximately still, perfectly still, held in place like a beam pinned to the backdrop of space. Across different telescopes, nights, stacking methods, weather, and calibration frames, the jet's orientation remains unchanged. It does not drift, it does not arc, it does not bow under rotational imprint. And to any astronomer, professional or amateur, that stillness is disturbing, because stillness implies order, and order, in something that should be chaotic, implies a cause we do not yet understand. Imagine holding a rotating sprinkler. The nozzle keeps turning, and the water fountains outward in a spiral. Now imagine that same sprinkler, but as it turns, the water draws a perfectly straight line into the air, never curving, never shifting, never acknowledging the motion beneath it. You would know instantly that something more than rotation was at play. Either the nozzle is locked in some precise orientation, or something is compensating for the motion in real time. Now scale that mental picture to an interstellar object tens of millions of kilometers away, surrounded by vacuum and solar radiation, accelerating slightly more than gravity predicts, and shedding gas in full sunlight. That is the discomfort 3I, Atlas, gives astronomers. Let's consider the natural scenarios first, not because they fit, but because scientific discipline demands it. Scenario 1. The jet emerges exactly along the rotation axis. In that rare alignment, rotation wouldn't produce spiraling. But the observed jet does not match the orientation of the presumed spin axis. The modeling attempts that try to force this explanation require contrived geometries. Not impossible, but deeply strained. Scenario 2. Multiple vents create an average straight line. If two or more vents fire in opposite directions, their combined patterns could appear straight, but the brightness profile, the collimation, and the persistence of the structure argue against this. There is no signature of multiple sources, no twin jets, no mirrored cones. Scenario 3. Image stacking artifacts. Long exposures can manufacture linear features through alignment choices, but this explanation collapses when independent observatories reproduce the same structure, when noise patterns differ, but the line remains, when even short exposures, those designed to avoid streaking, show a consistent direction. Natural possibilities exist, but they wobble. The jet does not. So if the rotation is real, and the jet is real, and the two are incompatible, what exactly is happening? Let's zoom in on the rotation itself. Cometary bodies tumble, they precess. Their spin states wander, as venting adds torque. Even 2I, Borisov, which was comparatively simple, showed measurable twist in its jet patterns. But 3I, Atlas, appears unnervingly composed. Its spin does not show chaotic change. Its jets do not respond to heating cycles the way volatile surfaces typically do. There is an emotional weight to something that behaves too cleanly in a universe that prefers mess, because mess is nature, order is uncommon, and unchanging order is something else entirely. Consider the timing of this jet. It was observed before, during, and after times when 3I, Atlas, should have been experiencing intense heating. Outgassing should surge, weaken, pulse, especially for an object inbound from cold interstellar space. But the jet does not pulse. It persists like a held breath. The simplest explanation that this is a highly collimated CO2 jet driven by shadowed subsurface ice fails to explain the directional stability. CO2 outflows are powerful, but they respond dramatically to rotation. They paint arcs in almost every observed comet. This one paints a line. Here is where astronomers begin to whisper, even if they don't publish. What if the line is telling us something simple but uncomfortable? Because if a jet maintains direction relative to the sun rather than the nucleus, that is weird. If a plane maintains direction relative to inertial space instead of the rotating body, that is weirder. And if a jet maintains direction despite all expected torques, all expected surface irregularities, all expected thermal inconsistencies, that's where the silence in research papers becomes louder than their text. This does not mean artificial, it only means unexplained. But unexplained at this level is rare. Let's look at the physics more concretely. A rotating body imposes angular displacement on any material leaving its surface. The speed of rotation and the velocity of the ejected gas determine the curvature of its path. For 3I, Atlas, based on its measured rotation period and assumed vent geometry, the jet should curve significantly within the first tens of thousands of kilometers. Instead, it appears straight at lengths approaching 1 million kilometers. 1 million. To achieve that naturally requires an astonishing coincidence. A vent placed so close to the rotational pole that outflow direction barely changes. But the light curve implies a different geometry, and the acceleration vector deduced from orbital deviations does not align with a strictly polar jet. The math resists compliance. The data refuses simplification. Something persists where nothing should. And that is why this single feature, the still jet of 3I, Atlas, matters. Not because it proves anything extraordinary, but because it refuses to be ordinary. This is the first moment in the story where the object pushes back. It tells us, gently but firmly, that it will not fit into frames built for predictable things, that it may require new framing altogether. There is no need for sensational language. Reality, when it contradicts itself, is dramatic enough. Some astronomers respond by caution, wait for more data. Others respond by analysis. There must be an angle we missed. And some, quietly, off record, respond by wonder. What if this is something we haven't seen before? Not something alien, not something engineered, simply something new, something that reminds us that the universe is under no obligation to be small enough for our diagrams, because every era of discovery begins with a mistake, a mismatch, a contradiction. And this contradiction rotation without imprint is the crack in the door, a narrow opening, a reason to keep looking deeper. 3I, Atlas spins. The jet doesn't. That is the riddle we begin with. Not a conclusion, a doorway. This isn't that comet. It's not C, 2023. A, 3. It's not C, 2025 N1. And calling it a comet might be the first mistake. Right now, there's a silent confusion, threading through astronomy forums, amateur communities, and even news headlines. Different objects, different timelines, different physics, all referred to by the same vague labels. Atlas, comet, interstellar visitor, that thing behind the sundae. But if we're going to understand what 3I, Atlas is, and why it matters, we have to start by removing the noise. Because what you call something changes how you look at it. And when something this rare arrives, clarity is not a luxury. It's the only way not to miss it. Let's be precise. 3I, Atlas, is not C, 2023, a 3. That's a different comet elliptical, long period, solar bound, expected to brighten dramatically near perihelion in 2024. It's a beautiful object, but it's not from interstellar space. It's not C, 2025 N1 either, sometimes confused online due to overlapping dates. That one's on a different trajectory entirely. Even the acronym ATLAS creates confusion, because multiple discoveries have emerged from the Atlas survey. Some are comets, some are asteroids, and only a tiny fraction are unbound. So what is 3I, Atlas, formally? It is the third interstellar object ever confirmed to enter our solar system. And that 3I means exactly what it sounds like. Interstellar object #3. The first was 1I, Oumuamua, discovered in 2017. The second was 2I, Borisov, in 2019. And now we have 3I, Atlas, first observed as A10 SVYR in 2023, and designated formally in 2024 after confirming its hyperbolic orbit. it is not bound to our Sunday. Its path slices through the solar system at a sharp angle roughly 59 degrees from the ecliptic and at a velocity that cannot be explained by gravitational perturbations alone. That's why it's called interstellar, not because we assume it came from another star, but because the data leaves no other viable explanation. And yet, despite that formal status, people continue to confuse it with other, less remarkable objects. Why? Because clarity demands effort, and most headlines don't make room for effort. There's also the naming problem. The name Atlas refers to the survey program that first spotted the object Asteroid Terrestrial Impact Last Alert System, but many other bodies have been tagged with that same survey name. The label becomes a smokescreen. That's why the prefix matters. The 3i tells you everything. This object does not belong here. Its orbit is not elliptical. Its energy is positive. Its inbound speed exceeds escape velocity. And unlike typical comets, it will never return. We get one shot, one approach, one outbound arc, and whatever questions it leaves unanswered, we'll have to live with. Let's pause here, because a quiet assumption has crept into conversations online that 3i, Atlas, is just another icy rock, just another pretty tale, just another chunk of ancient dust glowing in the Sunday. And that assumption is not just wrong, it's dangerous, because it blinds us to what makes this visitor different. Let's talk numbers. When 3i Atlas was first tracked, it displayed a strongly hyperbolic trajectory, with an eccentricity near 1.04, far beyond what planetary perturbations can explain. It entered the solar system at over 26 kilometers per second. It passed behind the Sun without fragmenting, and most importantly, its non-gravitational acceleration could not be modeled using standard cometry parameters. Even Borisov, with all its CO outgassing, behaved like a known class of comet. 3i, Atlas, doesn't. Its light curve is strange. Its chemistry is faint. Its behavior is cold. It doesn't flare dramatically. It doesn't fragment visibly. It doesn't scream for attention, but it doesn't obey either. This is where Avi Loeb enters the conversation. His team at Harvard-Smithsonian Center for Astrophysics has been closely monitoring 3i, Atlas, not because they believe it's artificial, but because they believe it's different enough to warrant the same rigor they gave to Oumuamua. And this time, we have more tools. Meerkat radio dishes, Vera Rubin surveys, the SKA pipeline, and above all time, we caught 3i, Atlas early enough to test, to listen, to model, to doubt our assumptions before they harden into false conclusions. There's a philosophical point here that's worth sitting with. When Oumuamua passed, we weren't ready. When Borisov passed, we blinked, and it was gone. Now, 3i, Atlas, is giving us a second chance, not at answers, but at better questions. And that starts by getting the name right. It's not a comet, it's not a hoax, it's not a space rock. It's 3i, Atlas, an unbound, rotating, line-emitting object with unexplained stability and solar system-defying motion. And when you name something correctly, it starts to behave differently in your mind. So let's clarify once and for all. 3i divided by Atlas is not equal to c divided by 2023. A 3i divided by Atlas is not equal to c divided by 2025. n1 I divided by Atlas equals a hyperbolic, non-returning, interstellar object with confirmed outbound vector. This is not tabloid science. This is orbital mechanics. This is a verified trajectory. This is the reason scientists stay up late, write in notebooks, stare at plots longer than they should, because in a world flooded with artificial noise, a signal this quiet stands out. If you take one thing from this story so far, let it be this. The object we're tracking is real. It's rare, and it's not what people think it is. It is not the fiery comet you'll see in clickbait headlines. It is not a doomsday rock or a UFO. It is something far more difficult and far more beautiful. It's a question with a name. And now that we've named it correctly, we can begin to understand what we're actually looking at. The universe has rules. We charted them, tested them, and trusted them. And then something arrived that broke too many at once. It wasn't loud. It didn't arrive with fire or fury. No explosion, no crash, no brilliant tail across the sky. Just a slow, deliberate drift. An object sliding through the solar system and disobeying nearly every law we thought mattered. Its name is 3I, Atlas. Its nature, still uncertain, but what's already done is undeniable. It broke things, not things you can touch, but the quiet scaffolding of assumptions beneath modern astronomy. The kinds of rules we forget are rules until something bends them. Let's look closely, because this isn't one anomaly. It's 12 silent breaks in the fabric of certainty. And they didn't come from a press release or speculation. They came from observation. First, its spin and jet don't match. Most rotating bodies that emit gas or dust show movement in their ejection paths. The jet spirals, the emission dances, spin imprints itself on what escapes. But 3I, Atlas, spins once every 16 hours, and the main jet remains still. A perfect line. No arc, no sweep, just a stable thrust that ignores the rotation of the object beneath it. That's like watching a fire hose mounted on a spinning wheel, yet the water flows in a straight line, undisturbed. It shouldn't happen. And yet, it does. Second, it accelerates without enough energy. If an object changes speed or direction, something must be pushing it. With comets, that's usually sublimation gas, escaping and nudging the body slightly off course. But when we model 3I, Atlas's trajectory, the acceleration is there. The change is measurable, yet the gases aren't. No major CO, no dramatic water vapor. The observed force is real, but the engine is missing. Third, the energy budget is broken. Every action has a cost. For a jet to produce thrust, it needs energy, sunlight, internal heat, and chemical reactions. But when we add up the energy required to produce the observed push and compare it to the energy available through sunlight and sublimation, we fall short. Not a little. By orders of magnitude, it's like finding a car cruising uphill with no fuel tank. Fourth, its light comes from the wrong side. Most objects brighten on the sunlit side. That's where heat hits, where ice vaporizes, where light reflects. But several images of 3I, Atlas, show the most intense brightness, its visible jet oriented away from the sun at unexpected angles. This isn't just a photographic trick. It's been confirmed across multiple observations, locations, and wavelengths. The brightest part of the object does not obey solar logic. Fifth, it stayed cold when it shouldn't. As interstellar objects approach the sun, we expect fireworks. CO2, outgassing, crystallization, fragmentation. But 3I, Atlas, behaved like a ghost. Faint, calm. Its infrared signal remained soft. Its brightness plateaued. No outburst. No thermal ignition. Even near perihelion, when solar energy should have boiled its surface, it remained eerily quiet. Sixth, the tail bends the wrong way. Comet tails point away from the sun, shaped by solar wind. But in high-resolution frames, 3I, Atlas, revealed a fainter structure, an arc of dust or material that seemed to bend sunward. Some called it an antitail, others an illusion, but the geometry persisted. If it's real, it suggests forces beyond solar wind are at play, perhaps magnetic alignment, plasma effects, or something more exotic. Seventh, it didn't fragment when it should have. The sun is cruel. Small, icy bodies, especially fragile interstellar ones, often don't survive close approach. But after 2 weeks of hiding behind the sun, 3I, Atlas, reappeared intact. No obvious breakage, no debris field, one clean nucleus, one continuous trajectory. It passed through a solar furnace and emerged whole. Eighth, its antitail geometry defies expectations. An antitail, a tail pointing toward the sun, is rare but known. It usually arises from Earth's orbital perspective, slicing through a dust sheet. But in this case, the angle, timing, and consistency didn't match standard predictions. The antitail of 3I, Atlas, lingered longer than expected, remained more defined, and contradicted simulations from previous models. Even among comet oddities, this was strange. Ninth, the 0818 cm signal was too clean. Detected by Meerkat, the 18-centimeter radio line corresponds to hydroxyl, a decay product of water. Its presence confirmed water, but the signal lacked noise. No spread, no typical emission tail, just a narrow, quiet frequency line. This level of purity is almost laboratory-like. Some astronomers whispered, "It's not the presence of water that's strange, it's how that water talks back." 10th, its brightness curve refused to change. From weeks before perihelion to weeks after, 3I, Atlas, maintained a remarkably stable light curve. No spikes, no dips, just a slow rise, a mild plateau, and a calm fade. Comets flash. They bloom. They flicker. This one didn't. Its light was steady, predictable, unbothered, as if it weren't reacting to sunlight at all. 11th, its spin refused to shift. Outgassing usually changes spin. Jets act like tiny thrusters, altering rotation over time. But even after months of venting, 3I, Atlas's rotation remained consistent. No measurable spin-up, no wobble, no drift in axis. It was as if something inside was compensating, balancing every push with a counterpush. 12th, its departure was too perfect. Once it rounded the sun and headed outbound, scientists expected a wobbly path. Jets, solar wind, and prior fragmentation usually introduce slight deviations. But 3I, Atlas depart. It looked deliberate. Each of these 12 points alone might be explainable. A modeling error, a data gap, an observational illusion. But all 12, in one object, across multiple instruments and months of review? That isn't noise. It's a signal of misfit, of non-belonging, of a visitor who didn't come to obey. The implications stretch deep. If 3I, Atlas, behaves like this, what else have we misclassified? How many comets were never comets? How many small anomalies were ignored because they didn't scream? There's a deeper silence here, not just observational, but philosophical. What do we do when a thing looks like it belongs, until it moves? What happens when the sky gives us a rule breaker and we pretend it's normal? Maybe this is the cost of hubris, of believing the laws we wrote would apply to everything, even visitors from outside. Or maybe 3I, Atlas, is just the first of many, a harbinger, a probe, or simply a mirror, showing us what it looks like when reality stops asking for permission. This object didn't explode, didn't send a message, didn't blink lights or bend space. It simply arrived, acted wrong, and left. And in doing so, it broke not just laws, but our comfort in believing laws are enough. It should have been obvious. Comets announce themselves. They sprout a coma, a halo of gas and dust, and trail a tail behind like a wedding veil in the void. When sunlight touches volatile ice, things happen. Outgassing, flaring, jets chaos in all directions. That's what we expect. That's what we're trained to see. But 3I, Atlas didn't give us that. Instead, it whispered, no coma, no dramatic tail, just motion, measured, verified, but unaccounted for. And that's what makes this so difficult, because something moved, but nothing visible pushed. It's one of the most stubborn mysteries in modern astronomy. How can a thing without a visible engine still accelerate? Let's walk through this carefully. From the beginning, astronomers were tracking 3I, Atlas's trajectory like any other visitor. Its orbit was hyperbolic, inbound from deep space, but as it neared the sun, the expected brightening the signature of a normal comet was curiously muted. At distances where others roared to life, this one merely hummed. It did produce light. Yes, and eventually, some sort of tail did emerge, but it was faint, intermittent, and directionally strange. What it never showed clearly was a coma, the bright, surrounding glow that should engulf a nucleus under solar stress. Hubble didn't see one. Pan-STARRS didn't see one. Even ground-based scopes, when stacking images, couldn't resolve the usual fog. And yet, the object moved, not just along its expected gravitational arc, but off it, slightly, persistently, quantifiably. This is where science tightens its grip. We measure motion, we fit orbits, we account for mass, drag, sunlight pressure, and sublimation. And still, something was off. When analysts plotted its position day after day, frame after frame, they noticed something peculiar. The fit was imperfect. A purely gravitational model didn't hold. The object drifted slightly off course. Not randomly, but in a consistent direction, as if something small but continuous was nudging it. That's when the term emerged, non-gravitational acceleration. A technical way of saying, there's a push here, but we don't see the hand doing it. In comets, That push usually comes from jets. Gas vents on the surface, primarily water vapor or carbon dioxide, turn to steam and act like thrusters. You can see them, you can simulate them, you can map the force. But in this case, the force was there, and the coma was not. The visible markers of active outgassing, the flares, halos, curling jets, were nearly absent. Even high phase angle images, where backlighting reveals the faintest emissions, showed almost nothing. This contradiction became sharper when radio astronomy entered the picture. A detection came in not from optical wavelengths, but from 18 centimeters, a signal in the OH band. That's hydroxyl, a dissociation product of H2O. When ultraviolet light hits water, it breaks it into hydrogen and hydroxyl speaks on the radio. The Meerkat array picked it up. A faint but sharp emission line, centered at 1,665, 1,667 megahertzes. No ambiguity. That signal only comes from one thing: water. So now we had the second piece of the puzzle. Water is there, but not glowing, not erupting, not swirling around the nucleus in a visible cloud. In other words, this object is leaking but without a leak. How? It's like watching steam rise from a teacup you can't see. You know the water is hot because vapor is climbing, but the cup remains invisible. Let's quantify it. Typical comets emit hundreds to thousands of kilograms of material per second near perihelion. They brighten, pulse, and shed volatile gas that's easy to detect. In contrast, 3I Atlas exhibited brightness levels suggesting far lower outgassing rates, and yet the non-gravitational acceleration was comparable to that of active comets. That's a mismatch. One theory suggests that the outgassing is collimated, focused through very narrow jets, not a fog, not a spray, but a laser-thin exhaust, possibly from buried pockets of CO2 or H2O under pressure. This would explain the lack of coma. If the jets are narrow enough and the vent geometry stable, the emissions could remain invisible, especially if composed of gas molecules that don't reflect much sunlight. Another possibility: size. If the nucleus is larger than we think, say 3 to 5 kilometers instead of under 1, then surface brightness would drop. We'd see less light, even with activity present. But radar and brightness data argue against that. The estimated size range puts 3I Atlas well below that threshold. Then there's the albedo question. Could the surface be unusually dark? Yes. Interstellar objects often carry organic rich coatings, tholin-like layers that absorb visible light. But this doesn't explain the absence of a coma. It just dims the object further. What we're left with is this. Something is releasing water. That water produces hydroxyl. That hydroxyl speaks on the radio. And yet we see almost nothing optically. No veil, no fog, no tail strong enough to match the push. In some ways, it resembles the famous paradox from another field. If a tree falls in a forest and no one hears it, did it make a sound? Here, if a comet vents into space and no one sees the gas, did it still thrust? Yes, because we measure the motion, we track the deviation, and the object is undeniably being pushed. But by what? By whom? The absence of visible coma doesn't make this less real. It makes it more disturbing. Because in science, when data and visibility diverge, we learn something new. Or we're missing something old. What if this is an old mechanism? One we've misclassified for decades. Low-level outgassing with high directionality, a sort of silent mode for certain objects. It wouldn't need to be artificial, but it would demand a rewrite of what we call active. And yet, the artificial hypothesis lingers. Some have noted the peculiar steadiness of the motion, the lack of tumbling, the clean, single-axis vector of the non-gravitational push. It's not proof, but it's not nothing. We're now in a territory where even cautious scientists admit we have no good explanation, only models that don't close. The coma was expected. It didn't appear. The tail was expected. It was weak and wrong-shaped, and motion, measurable, undeniable motion, happened anyway. Maybe 3I, Atlas, is a messenger of silence. Maybe it's a mirror to our assumptions. Maybe it's both. But what's clear is this. Something moved, and we didn't see the cause. Something pushed, and the push left no plume. That is not nothing. That is a clue. And when the sky gives you a clue, you don't look away. You look deeper. You listen for what didn't show up. You draw lines around absence. You chart motion where there's no visible force, because sometimes the story is not told by what blazes. It's told by what refuses to burn. It's one thing to be surprised by motion. It's another thing entirely to be surprised by its consistency. Comets spin. That's not debated. Most of them tumble, in fact, some slowly, some erratically, but all obey one fundamental truth. When they rotate, their jets wobble. The jet orientation follows the spin. The outgassing source shifts with time, just as a rotating lawn sprinkler moves the direction of the water spray. So what happens when a comet spins, but the jet doesn't move? That's what 3I, Atlas, is doing. It is rotating. We can see the spin pattern in its light curve, a slow, asymmetric dimming and brightening that tells us it turns. The current estimate is between 8 to 12 hours per full rotation. That's well within range for a comet of its size, and yet something isn't sinking. The jet direction, as inferred from both tail orientation and the trajectory of non-gravitational acceleration, remains stable. Not fluctuating, not processing, just steady. It's like watching a rotating fire hose that never changes the angle of the spray. The water jets forward as if the nozzle is nailed in place even while the base spins. This is the paradox. In the mechanics of real bodies in space, precession is expected. The jet vector should follow the local orientation of the vent. If the nucleus turns, the exhaust path arcs. The net force direction shifts. This introduces oscillation into the orbit, tiny, trackable wiggles. It also creates instabilities in long-term motion. But 3I, Atlas, refuses to follow that playbook. Its jet acts as if it is decoupled from the rotation, as if it exists outside the object itself, or worse, as if the spin axis and the jet vector are perfectly aligned and perfectly maintained over weeks and weeks of solar heating. Let's be clear, that's nearly impossible. No natural surface is that uniform. No comet nucleus is that symmetrical. Thermal stress, surface cracking, uneven material distribution, all of these should nudge the vent slightly off the axis or alter its power with time. Instead, we see constancy. The inferred direction of the reactive thrust has not deviated. The small shifts in trajectory from non-gravitational forces point the same way day after day, week after week. If the spin is real, and it is, then the jet must either be on the pole itself or constantly corrected to stay aligned. Let's examine the first possibility, a polar jet. This would mean the vent is located directly at the north or south rotational pole of the object. So, as the body turns, the jet always points in the same inertial direction. It's theoretically possible, but it's incredibly unlikely. Why? Because forming a vent exactly on the spin axis requires a coincidence of thermal symmetry, material distribution, and early outgassing history that borders on miraculous. Comet nuclei are chaotic. Their spin axes shift over time due to torques from uneven jets. Surface layers erode unpredictably. To maintain a polar vent under such conditions would require an object to be finely tuned or finely stabilized. Which brings us to the second, more unsettling possibility. Something is correcting the jet. This would imply feedback, a mechanism that senses deviation and adjusts accordingly. Nature doesn't typically do this, unless the internal structure is rigid and capable of channeling pressure through fixed conduits like nozzles or shafts. But that starts to sound less like a rock and more like a device. Now, before the leap into wild speculation, let's consider an intermediate hypothesis. What if the jet is not just a vent but a collimated, anisotropic outflow from deep beneath the surface, guided by internal geometry? Some icy bodies are known to have cold volcanoes, cryogeysers, that channel subsurface volatiles through narrow ducts. If such a structure existed within 3I Atlas, it might produce a persistent outflow vector, resistant to surface changes. Still, that wouldn't explain the stability of direction unless the internal channel were fixed along the spin axis. Again, we loop back to alignment. The problem isn't just that there's a jet, it's that the jet doesn't wobble. It doesn't follow the spin, it doesn't proceed, it doesn't show the hallmark deviations of a rotating emission source. This raises deeper questions. Could the object's mass distribution be somehow so perfectly balanced that its axis never shifts? Could the spin be slowing down or tidally locked in some way, reducing the effect of precession. None of these explains the core issue. Why doesn't the jet change direction as the comet turns? There are analogies in engineering reaction wheels in satellites that stabilize orientation, or gyroscopic systems that maintain spin alignment. But comets don't come with firmware. And yet, 3I, Atlas, behaves as if it's executing an attitude control protocol. Even if it's purely natural, this object forces us to rethink something. Is our model of comet venting too simplistic? Are we underestimating the role of internal topology in shaping outgassing? Or are we witnessing something we're not equipped to classify? Because if the jet is aligned and persistent, if it doesn't precess despite rotation, then it isn't just a comet with unusual behavior. It's a challenge to mechanical expectations. Physics tells us that torque results from off-axis thrust. If thrust remains aligned and the spin remains constant and there is no visible correction, then either we're missing something or the rules don't apply here. Either answer should make us uneasy. We're not just tracking motion anymore, we're tracking intent, or the illusion of intent. Some skeptics argue that it's a fluke of observation, that we simply haven't watched long enough to see the wobble. But we have. Hundreds of hours of telescope time, multiple angles, multiple instruments, same result: stable spin, stable thrust, unstable understanding. This isn't just an astronomical oddity, it's a philosophical one. Because every law we write about motion assumes randomness unless order is imposed, and this object imposes order without explanation. It doesn't spin like it should, it doesn't vent like it should, and it doesn't proceed like anything we've known. So we have two choices. We can force the data to fit our model, or we can admit the model is incomplete. That's the crossroad of science. Not when we find the unexpected, but when we find it again and again, and still call it impossible. What kind of object stabilizes a jet across a rotation cycle? What kind of system resists entropy? What kind of comet, if it is a comet, teaches stability through silence? We don't know, but we keep watching, because when the jet doesn't precess, the mind does. And maybe that's the real force at work here, not gravity, not thrust, but doubt. First came the silence, then came the line. In the vastness of space, you don't wait for echoes, you wait for alignment. And on a cold September morning in 2025, something aligned. Not a light, not a flare, a line. A line at exactly 18 centimeters from a place where no signal should have come, from a visitor we still don't understand. And it wasn't a metaphor, it was chemistry. The 18 centimeter OH line isn't a suggestion, it's a signature. It means one thing: water. More precisely, it means the breakup of water. In the cold of interplanetary space, ultraviolet photons strike water molecules ejected from cometary surfaces. The water splits into hydrogen and hydroxyl, OH. The OH molecule then emits at a very specific frequency, 1,665 and 1,667 MHz, together forming the 18 cm radio line. It's not theoretical, it's not abstract, it's detectable, but only if you're listening, and only if the water is real. That's what made this signal matter, because the listening wasn't accidental, it was planned. Meerkat, one of the most sensitive radio telescope arrays on Earth, was aimed directly at 3I, Atlas, not to catch a flare, not to catch a mystery, but to test a hypothesis, that behind all the strange movement, all the out-of-place energy, all the whispering physics, it was something simple, something familiar, water the oldest traveller. And when the data came in, there it was, faint, but clear, a spike at 1,665 MHz, a twin at 1,667, the OH line. For scientists, it wasn't a scream, it was a confirmation. This wasn't just a rock, it wasn't an alien artifact, it wasn't a camera trick or a sensor glitch. It was a body that, at its core, was shedding water into the void. A comet, but not just any comet, an interstellar comet. We've seen OH before, 2I. Borisov had it, though it also gave off more exotic gases like CO and CN. But 3I, Atlas, was more cryptic. For weeks, it refused to show a visible coma. Its tail was unstable. Its surface was unusually dim, and still it outgassed. Not with a spectacle, but with truth. Meerkat's detection did more than confirm water. It rewrote how we verify visitors from beyond. Because, unlike light, radio signals don't lie. They're not scattered by dust. They're not biased by albedo. They carry the raw fingerprint of molecular transition. This line, the OH18cm line, is the decay product of life's solvent. Not life itself, but the solvent that carries it, that builds clouds and carves valleys and binds strands of carbon into memory. The line means presence. Not in the philosophical sense, but in the chemical one. Presence of water vapor, presence of energy to lift it, presence of heat, presence of possibility. Suddenly, the story of 3I, Atlas, was no longer a story of speculation. It was a story grounded in spectra, in physics, in a line that connects us across the dark. The detection had other implications too. It validated the estimates of outgassing-driven motion. We knew the object was accelerating slightly off course. Non-gravitational motion was evident in its orbital changes. But until the OH line, that motion could have been due to other volatiles like CO2 or CO. Now, we had direct proof. Water was the engine. This made 3I, Atlas, more Earth-like in composition. Less exotic, perhaps, but in a strange way, more profound, because it meant that water, the same molecule that blankets our planet, that fills our cells, that powers our storms, was also the connective tissue of the galaxy. It had left another star system. It had crossed interstellar space. It had endured radiation, temperature swings, and isolation, and it had survived, waiting for one more sun to warm it, one more telescope to hear it, one more species to notice. It's easy to overlook what this means. We didn't just detect water, we detected interstellar water, water from another system, possibly another sun, possibly older than our own oceans. It evaporated into a vacuum billions of miles from home, and yet its voice arrived, not in English, not in metaphor, but in frequency. A precise, narrowband hum that said, "I was here, I was warm, I was liquid, now I speak light." This is what science dreams of, not headlines, not aliens, not answers, but proof. Proof that the strange is still natural, that mystery doesn't mean magic, that what comes from elsewhere can still obey the laws we know while inviting us to learn more. It's important to say what this signal didn't mean. It didn't mean life. It didn't mean intelligence. It didn't mean design. But it did mean structure, and chemistry, and process. It meant that our models, at least in part, held. That the thrust we measured, the light we puzzled over, the curves we calculated weren't just guesses. They were leading us somewhere, to a detection that mattered. Because in the age of noise, a narrow signal is hope. There was hope that our methods still work, that looking still matters, that behind every anomaly might still be a truth not yet revealed. But waiting, Meerkat wasn't the only one listening. Now, other arrays have joined in. FAST in China, the VLA in New Mexico, the SKA Pathfinders. They're all watching the same line, because it's not just proof of water, it's proof that we can catch a message, not from minds, but from molecules. A comet doesn't mean to speak, but physics gives it a voice, and telescopes give us ears. The 18cm OH line is now part of the standard playbook. When the next object comes, and it will, we won't wait. Well, tune to the frequency. Well, listen. And maybe, just maybe, the next signal will say more. Or say it louder. Or say it with isotopes that carry the accent of another star. But until then, 3I, Atlas, gave us something rare. Confirmation. Not speculation, not theory, but a number, a shape in a spectrum, a spike on a screen that said, "This is real, this is water." From there, now here, now gone, but heard. And once something is heard in science, it can't be unheard. It becomes a reference point, a calibration mark, a memory we build systems around. That line, 18 centimeters long, rewrote 1,000 doubts. It didn't solve the mystery, but it made the mystery worth solving. And that changes everything. It should have shattered. That was the expectation. The models said so. The physics said so. Even history said so. A fragile body, hurtling from interstellar space into the inner solar furnace, should not survive. And yet, it didn't explode, it didn't fracture, it didn't even flinch. On the 29th of October 2025, 3I, Atlas, passed its perihelion, its closest approach to the Sun, at 0.34 AU, just a third of the Earth-Sun distance. At that range, solar radiation is 9 times stronger than what we receive here. For ordinary comets, it's a trial by fire. For interstellar visitors with no insulation, no heritage, no tailwind of dust to protect them, it's a death sentence. And yet, it lived. Why? To understand the scale of the paradox, we need to walk through the math. Let's start with energy. Thermal budget, the fire it shouldn't have survived. At perihelion, solar irradiance on 3I, Atlas exceeded 12,000 Wm squared. That's enough energy to melt metal, sublimate ice instantly, and ignite internal pressure differentials that can tear a porous object apart. Now apply that to a surface tens of kilometers wide, rotating every few hours, absorbing heat asymmetrically. Comets aren't solid steel. They're loosely held piles of dust, ice, and void. In thermal models, this porosity is catastrophic. Heat penetrates quickly, but dissipates unevenly. Hot pockets form inside, pressure builds, and then crack. Split. Explosion. We've seen it happen. Comet Ison, 2013, vaporized near perihelion, disintegrating just before closest approach at 0.012 AU. C. 2010X1, Elenin, destroyed by sunlight before it even reached its closest point. C. 1999, S. 4, Linear, broke into fragments and dissipated weeks after perihelion due to thermal stress. These weren't interstellar objects. They were native comets with predictable materials. And still, they died in the heat. So why not 3I, Atlas? That's where things get strange. The thermal model breakdown, standard cometary survival models, rely on 5 major variables. 1. Albedo reflectivity. 2. Thermal inertia. 3. Rotational period. 4. Size and surface area. 5. Outgassing vent strength. Let's test each for 3I, Atlas. 1. Albedo. Measurements indicate a low albedo around 0.04. That means it absorbs about 96% of the sunlight that hits it. More heat in, more danger. 2. Thermal inertia. Thermal inertia defines how quickly an object's surface adjusts to changing temperatures. Low inertia means fast heating and fast cracking. No anomaly detected here. 3I. Atlas behaves like other comets. Low inertia, fast flux. 3. Rotation. Here is where it gets interesting. Its light curve suggests a rotation period of several hours, meaning that parts of its surface spend long enough in the sun to heat up dramatically and not long enough in the dark to cool down. This creates a thermal gradient, hot and cold regions tugging at the internal structure. 4. Size. Estimates place its nucleus at 2 to 3 kilometers, comparable to many comets that didn't survive. Size doesn't help. In fact, mid-size objects are more vulnerable, large enough to store energy, small enough to lack structural integrity. 5. Outgassing vents. Minimal. Its coma was faint, its jets were weak. This is critical. In other comets, sublimation relieves internal pressure vents, act like release valves. But 3I, Atlas, had no obvious venting at perihelion. In other words, the pressure built up and had nowhere to go. So again, why didn't it explode? The energy deficit paradox. One of the more bizarre features of 3I Atlas was its lack of activity near peak heating. You'd expect sublimation to spike, you'd expect brightness to increase, you'd expect debris. Instead, it passed perihelion with no fragmentation, no brightness flare, and no coma expansion. Energy was going in, but what came out? That's the mystery. There was no matching energy signature, no thermal emission to account for what it absorbed. This led researchers to propose an unsettling possibility. The energy was being stored or redistributed in a way we don't understand. Let's call this the energy deficit paradox. Some suggested it might have unusually high tensile strength, like a monolith of metal or carbon, but radio reflectivity didn't support this. Others thought it might be hollow, with energy bouncing inside, yet its rotational stability argued against a hollow core. Some posited a kind of latent phase change material, something that absorbs energy without changing shape like aerogels or phase-shifting polymers. But that's speculative. There's no evidence that such materials occur naturally, which leaves us in the dark, literally. Because 3I, Atlas, absorbed the heat of 1,000 suns and whispered back nothing. Sublimation, the vanishing act that didn't happen. Sublimation is the phase transition from solid to gas, what comets do best. It powers tails, it drives spin, it tears nuclei apart. For 3I, Atlas, models predicted rapid sublimation of surface water ice at 0.34 AU. Surface temperature estimates exceeded 270 K, 3 degrees Celsius, well above the point at which cometary ice boils off in a vacuum, yet observations showed no surge. This implies either it didn't have much ice on the surface, the ice was buried too deeply, or the surface material was unusually insulating. But even buried ice should sublimate under sustained heating. The absence of that event forces us to reconsider assumptions about the surface composition. Could it have been covered by a crust, a hardened shell of organic dust that shields interior ice? Yes, but crusts tend to crack under stress. Still no cracks, no fragments, the object held together like a single piece of reinforced mystery. Perihelion, the moment we held our breath. For a brief moment in October, every telescope that could see was pointed at a rock we thought might not survive. The world waited. Would it flare? Would it split? Would it vanish? Instead, it emerged from the other side, whole, intact, and unchanged. And in that stillness was a kind of scream, because every silent survival forced a recalibration of what we thought comets were made of. This wasn't just a survivor, it was a challenge. It said, "I passed your test, now revise your theory." Legacy of the non-explosion. We talk about cosmic violence as spectacle, fireballs, breakups, dust trails across the sky. But this was a quieter defiance. It didn't explode, it didn't entertain, it endured. And in doing so, it undermined every thermal model we trusted, not fatally, but sufficiently to plant doubt, to make us ask if interstellar objects are more robust than we believed, or more strange. Maybe 3I. Atlas is built from ancient, pressure-hardened materials. Maybe it formed under different gravitational conditions. Maybe it's not a comet in the traditional sense at all. Whatever the truth, its non-explosion is now part of our records. A data point against expectation, a survivor where none were expected, and perhaps most importantly, a warning. The universe doesn't owe us predictability, that objects from other stars play by rules we haven't written, that when fire doesn't consume, we shouldn't relax, we should investigate, because something that should have died and didn't has more to tell us than something that vanished as predicted. It left no trail, no plume, no dust, no lingering echo of motion, just a quiet shape, drifting alone through the dark. And for astronomers trained to see the sky not as dots but as stories of motion, this silence was deafening, because comets, by definition, announce themselves. They flare, they leave trails bright, decaying whispers of ice and rock turning to gas, forming tails that point away from the sun, even when the nucleus hides in shadow. But this one didn't. 3I, Atlas, moved across our field of view like something trying not to be seen. And the harder we looked, the more we realized it wasn't just quiet, it was missing the very signature that defines a comet. This isn't a poetic metaphor. It's an observational fact. Dustless, fragmentless, featureless. In astronomy, we don't just take single snapshots. We stack images hundreds, sometimes thousands of frames, taken over hours or even days aligned to the motion of the target object. This technique enhances faint features, tails, halos, debris fields, even tiny fragments left behind by previous outbursts. It's how we mapped the delicate twisting tails of Comet Neowise. It's how we watched Comet Elenin dissolve. It's how we knew C, 2019 Y, 4 Atlas, had broken apart even before Hubble confirmed it. But when we stacked 3I, Atlas, there was nothing. No tail, no debris cloud, no fragment train, no anti-tail, no dust sheet, no reflected sunlight off suspended grains. just the nucleus. And even that was dim. We even used the best tools we had. The Vera Rubin Observatory flagged it in multi-night sequences. JWST and Hubble attempted deep exposures. Ground-based telescopes used narrowband filters for common gas emissions. But in every band, in every image, in every attempt to find the story behind the motion, silence. The object remained point-like. The coma, if it existed, was below all known detection thresholds. And the background? Empty. The trail that should have been there. To appreciate the weirdness, imagine this: an interstellar object traveling tens of kilometers per second, experiencing solar heating 9 times stronger than Earth, and yet producing less visual evidence than a dying satellite. Standard thermal sublimation of water ice under perihelion heating should generate not just gas, but dust ejection, tiny grains lifted by outgassing pressure. These grains, when released, scatter sunlight and form visible trails. If the surface were icy, there should have been a tail. If it were dusty, there should have been a coma. If it cracked, there should have been debris. But none appeared, so we looked deeper. What the shadow didn't reveal. One of the oldest tricks in the observational book is backlighting. Observe an object when it's positioned opposite the sun, so any faint trail is illuminated from behind. In theory, even a thin dust trail would glow like a ghost. We timed observations around this geometry. We enhanced contrast. We modeled light scattering across multiple angles. Still, nothing. There was no indication of shadowed debris, no glints of trailing fragments, no soft echo of material suspended in its wake. Just a moving point, isolated, sharp-edged, lonely, a silent path through solar wind. The sun is not passive. Its outflow solar wind, radiation pressure, and magnetic turbulence shreds fragile material. This is why many comets flare on approach and fragment after perihelion. We assumed that if 3I, Atlas, had any loose material, it would be peeled away like bark in a storm. But it sailed through the chaos as if it were armored. No peeling, no scattering, no visible sign of erosion. It seemed to repel the very processes that make comets glow, and yet it moved. It accelerated. It vented, subtly. We know this because its orbit shifted in ways that only outgassing can explain. But that outgassing left no visible sign. It was invisible propulsion. A ghost force. This contradiction became one of the defining puzzles of 3I, Atlas. When comets forget how to be comets, a trail is not just a pretty detail, it is forensic evidence. It tells us what the object is made of. It reveals structure, rotation, and fragmentation history. It allows trajectory tracing, especially for potential Earth crossers. 3I, Atlas denied us all of this. It behaved like a comet on paper, based on its trajectory and acceleration, but visually, it behaved more like an asteroid or a spacecraft. And this comparison became hard to ignore, because spacecraft, too, lack trails and less venting. Spacecraft move smoothly, cleanly, in defiance of celestial drama. So, we were left in the strange position of describing an object that flew like a rock, but moved like a comet, and trailed like nothing. In astronomy, such contradictions aren't just anomalies. They are irritants to the model. They force revisions. They are humbly confident in math, and they isolate the object from categories. 3I, Atlas, didn't just lack a trail. It lacked a tribe. What kind of object doesn't bleed light? The trail of a comet is light reflected, scattered, polarized, refracted. We see trails not because we see the dust itself, but because we see what light does when it meets that dust. So what if the dust was non-reflective? What if it were made of carbon black aggregates, absorbing 99% of light, invisible in all but thermal infrared? Even then, we should have seen something. The thermal emission would show up in JWST bands, but we didn't. What if it didn't eject dust at all? Then it wasn't a comet. What if it were only gas, with no solids? That's rare. CO, 2 jets. Yes, but no solid carriers? That's unheard of. What if it wasn't ejecting anything at all, and the motion was from something else? That we're not ready to say. But the lack of trail doesn't just raise questions about its current state, it raises questions about its entire history. Because objects leave trails, even dead comets, even rocky asteroids, accumulate a cloak of interaction dust from collisions, particles from past outbursts. To leave no trail at all, that implies a clean past, or a different path through the galaxy, or shielding. Isolation is not just about motion. In the end, the strangest part wasn't what we saw, it was what we didn't. No trail means no context. No physical trail, no behavioral trail, no chemical trail, just a body that moved through our system and refused to leave a footprint. And in science, footprints matter. They are how we verify theories. They are how we classify. Without one, 3I, Atlas becomes unclassifiable. It moves alone. It reveals nothing. It disobeys silently. That's not just isolation. That's deliberate uncooperation with natural patterns. And so, in the dark, 1,000 light years from home, an object passed through our house and refused to wave, refused to shed, refused to burn. It just moved and was gone. There is a comfort in the improbable, a discipline in resisting the strange explanation, and a principle older than astronomy itself: never attribute to the extraordinary what the ordinary can still explain. Because for every object that defies our categories, there's a model imperfect, incomplete, but honest, that tries to stretch, not snap, the known. So let's ask it plainly. What if 3I, Atlas, is natural? What if every contradiction, the motion without trail, the energy budget mismatch, the radio signal can be explained not by something artificial, but by the far edge of nature itself? That's the question science is supposed to ask. Not what if it's aliens, but what if we're just not looking clearly enough at what nature already does? Let's walk through the possibilities. Slowly, with both feet on the ground. 1. The CO2 jet hypothesis. At the center of the current natural model is this idea. 3I. Atlas is venting carbon dioxide, CO2, not water. Unlike H2O, which needs to be closer to the sun to sublimate, CO2 can outgas at much colder temperatures and at greater distances. This explains several things. Why did the object begin exhibiting non-gravitational acceleration even before perihelion? Why the 18 cm OH line appeared late and weakly? Because water was not the dominant compound. Why were visual signs minimal? CO2 outgassing often lacks dust emission. The gas jets are nearly invisible in visible light. We've seen this before. Comet 29P, Schwarzmann-Wachmann, for example, shows high CO2 activity in deep space with minimal coma brightness. So the precedent exists. If 3I Atlas were a CO2 dominant object formed in a region rich in volatiles but poor in dust, that alone could account for the ghost-like visibility, the early acceleration, and the lack of a trail. It's not dramatic. It's not alien. But it's physics. 2. An unusual shape can mimic artificial dynamics. One of the more compelling data points about 3I, Atlas, is the consistency of its jet direction, despite an apparent rotation. This creates a paradox. How can the object be spinning, but still produce non-precessing jets? Here one answer: the shape. If the object is highly elongated like a cigar or pancake, and the spin axis is aligned with the jet direction, the visible effect would be that the jet appears stable, even if the body rotates. This isn't hypothetical. 1I Oumuamua's strange tumbling motion and light curve led to similar suggestions that its shape exaggerated observational effects. If 3I, Atlas, is spinning around its long axis, and jets are emitted from the poles, then the precession is minimized. The outgassing appears steady. No exotic technology. Just a shape we rarely observe because these objects are faint, fast, and often missed. 3. Known mechanisms can produce unexpected stability. Skeptics ask, how can a loosely bound object survive such a close solar approach without fragmentation? But we've seen cometary nuclei hold together under far worse. Thermal modeling of comet Ison in 2013 showed that while most observers predicted disintegration, the core structure allowed for survival until deep tidal forces near perihelion finally pulled it apart. But not all objects behave that way. The thermal inertia of a nucleus, its ability to conduct and retain heat, plays a huge role in whether it fractures. If 3I, Atlas, had a low porosity surface, high thermal conductivity, rocky or metallic compounds, and limited internal pressure pockets, then it could easily have survived its solar encounter intact. Its lack of flare, lack of outburst, could signal not mystery, but maturity, an object that had already outgassed most of its volatile load across galactic time. Survival isn't miraculous. It's material science. 4. Interstellar origins don't equal intelligence. There's a tendency to treat interstellar as synonymous with alien. But space is big enough for wandering rocks to exist by the trillion. 3i. Atlas's incoming trajectory was hyperbolic, that is, not gravitationally bound to the Sunday. Its velocity and inclination point to origins outside the solar system, likely ejected from another star system during planetary formation. This makes it rare, but not unprecedented. 2i. Borisov was interstellar. 1i. Oumuamua was interstellar. The more we look, the more we'll find. The galaxy doesn't just export energy, it exports debris, and the vast majority of it will be natural. Icy fragments, rocky cores, eroded bodies that spent eons between stars. To assume otherwise is to dismiss the billions of years that nature had a head start. 3i. Atlas may be strange, but strange does not mean sentient. 5. Noise is not a signal. Much has been made of the 18 cm radio detection from Meerkat. The OH line, split at 1,665 and 1,667 MHz, was clear, but some observers reported anomalous features, asymmetries, narrow band shifts, small periodicities. Was it a signal? No. Analysis showed that the spectrum, though intriguing, was consistent with known OH emission lines under outgassing conditions. The shape of the line profile, the redshift, and the Doppler broadening these can all arise from a directed jet in a rotating frame. Radio telescopes often pick up resonance harmonics or local interference, and Meerkat operates in a dense region of the spectrum where terrestrial and cosmic noise overlap. No information was encoded, no signal repeated, no modulation beyond what sublimating gas would produce. To call it a message is poetry. The absence of debris may be the final natural clue. If 3i Atlas is shedding nothing, perhaps it has nothing left to shed. It may be a fossil comet, a core that long ago lost its volatile skin. This process, called mantling, involves the gradual build-up of non-volatile crust, insulating layers of refractory material that suppress further outgassing. Such objects become dormant comets, nearly indistinguishable from asteroids. But sometimes, buried pockets of CO2 remain. A small fissure, a thermal shock, or rotational stress could cause venting through a narrow channel, just enough to produce the orbital shift we observed, but not enough to eject visible dust. If this were the case, 3i Atlas would be the first fossil comet detected in interstellar transit. Not artificial, just old and quiet. Why science must defend the ordinary? The duty of science is not to be boring, it's to be rigorous. And rigor means defending the mundane explanation when it still fits. 3i Atlas is peculiar, but the peculiar is not yet the supernatural, not yet the artificial. Our best models, CO2 jetting, fossil comet mantling, elongated body spin alignment, may not explain everything, but they explain enough to buy time for new data, not buy into fantasy. In a universe where trillions of rocks drift between stars, the burden of proof lies on the extraordinary, not the slow, hard path of confirmation. Let us keep walking that path, even if it means accepting that what passed through our skies was not a probe, but a mystery still shaped by natural laws we don't yet fully grasp. And that, too, is a kind of wonder. There's a line science rarely crosses, not because it's forbidden, but because it risks opening doors that lead nowhere, or worse, doors that lead somewhere we're not ready to follow. But sometimes, the data doesn't whisper the familiar. It leans in and asks a question so sharp, so silent, that ignoring it would be unscientific. So here it is, not as a declaration, but as a possibility. What if 3i Atlas isn't natural? Not a comet, not a rock, not a fossil from another star's long-dead nursery, but a design, not a message, not a weapon, not a miracle, just something made. The kind of made that doesn't shout. It moves with subtle purpose. It follows the rules just closely enough to be missed until you notice it didn't break the rules. It bent them, not enough to scream artificial, but enough to make the silence feel strategic. Let's follow that thread. 1. The thrust that didn't scatter. A natural object, when venting gas, behaves chaotically. Dust escapes. Jets erupt unpredictably. Rotation alters orientation. Coma expands with distance and sunlight. But 3I, Atlas didn't do any of this the way it was supposed to. Its outgassing produced no observable coma. Its acceleration curve was smooth, almost controlled, and the direction of thrust didn't precess with spin. Now ask yourself, if you were designing an interstellar vehicle that needed to adjust trajectory using sublimation, what would you want? A fuel source that activates without combustion, non-visible emissions to reduce traceability, a stable vent orientation regardless of spin, a low-energy profile to avoid detection. That's what 3I, Atlas gave us. To be clear, CO2 venting could mimic some of this, but not all of it, and not with this degree of directional precision. When Avi Loeb published his initial suspicions about Oumuamua, he focused on its non-gravitational acceleration without visible mass loss. 3I, Atlas one-upped that. It showed acceleration with radio-confirmed outgassing, but still no trail, no debris, no visible alteration. That's a finely tuned system. Too finely tuned. 2. The spin that didn't wobble. Most natural bodies, especially elongated ones, tumble. Rotational dynamics at this scale are dictated by chaotic histories, collisions, tidal torques, and uneven heating. But if 3I, Atlas, were tumbling freely, then jet emission would rotate with it. The result? A spiral trail, varying thrust vectors, precession in the observed orbit. But we didn't see that. The direction of acceleration remained fixed, not just mostly fixed, remarkably stable. Over weeks. There's a term in engineering, spin lock. It's the process of stabilizing a rotating body so that one face always points in a particular direction, much like how satellites maintain antenna alignment while spinning. Could 3I, Atlas, be doing something similar? If the jets are precisely placed relative to the center of mass, if the structure internally routes volatile ejection through calibrated vents, then you can maintain thrust without changing spin. In fact, you can use spin to balance forces. Imagine an interstellar object built not with engines, but with knowledge of rotational harmonics. Let the physics do the work. Let sublimation become steering. That's not fantasy. That's aerospace. 3. The budget that didn't break Harry's, where the energy modeling becomes problematic. Based on proximity to the Sun, we can calculate how much thermal energy 3I, Atlas, should have absorbed. That number is high, so high in fact, that most known comets of comparable size would have fractured, exploded, or undergone rapid disintegration. But 3I, Atlas, emerged from perihelion, not just intact but still accelerating. The sublimation curve did not align with standard thermal models. Its energy loss was less than expected. Its structure held together better than expected. Either it's made of a material with unusually high tensile strength, or it has internal mechanisms for managing thermal load. Think about that. Not a heat shield, not a hull, but layers, chambers, and routing structures are designed to channel solar energy, not absorb it. Some researchers suggested this for Oumuamua, that it may have had a metallic or porous surface optimized to reflect light or radiate heat away. With 3I, Atlas was seeing an object that didn't shatter, didn't erupt, and didn't slow down. Instead, it behaved like something with a designed survivability profile. A traveler who knows how to pass through systems without dying in them. That's not natural. That's functional. 4. The radio that didn't repeat. Let's revisit the OH-18cm line. Yes, it's a known indicator of water-based outgassing. Yes, Meerkat's data matches expectations for natural emission. But look closer. Some anomalies were detected in line symmetry, slight deviations in peak alignment, potential harmonic features. These could be artifacts, or they could be what in communications engineering we call a carrier, a signal that rides inside another. Now, there's no direct evidence of message content, no modulation beyond noise thresholds, but it's worth asking, if a civilization wanted to test low-energy interstellar broadcasting, would they embed it inside a natural molecule's frequency? Why not choose OH, the same line any intelligent observer would already be watching? Broadcasting at 1,000, 665 megahertz is camouflage. It's like whispering under the cover of wind. Again, this isn't proof, but neither is it a coincidence that this is the first time we've ever captured interstellar radiochemistry directly from a passing object. If someone wanted us to notice them without scaring us, this would be the way. Don't shine a laser, don't land a probe. Just pass by, leaving only data, like a signature in steam. 5. A vehicle without a mission. The most haunting thing about 3I, Atlas, isn't its behavior. It's its indifference. It didn't slow down. It didn't orbit. It didn't alter course after detection. If it's a probe, it's not here for us. But that might be the point. Maybe it's not meant to communicate. Maybe it's a passive recorder, drifting through systems, cataloging chemical fingerprints, mapping stellar winds, logging gravitational fields. Maybe it transmits only when near a star, when solar power becomes available. Or maybe it's already done transmitting, and now it coasts forgotten. Some satellites in Earth orbit have been silent for decades. Some interstellar craft we launched like Voyager are nearing the edge of power. 3I, Atlas, could be one of billions of relics. Old, silent, persistent, built not for speed or glory, but for endurance. This reframes the mystery. It doesn't want to be seen. It's just not hiding well enough anymore. 6. The dread in the design. All of this leads to a question that chills more than it excites. If it is artificial, then it's not the first, because no one sends their prototype to another star system. This would be an old technology, part of a larger network, or the remnant of a vanished architect. And we'd be late, watching not a message, but an echo, not a visitor, but a forgotten pathway. This possibility doesn't need aliens in metal ships. It needs only time. A civilization millions of years old doesn't announce itself. It just leaves behind debris that's smarter than anything we've made. 3I, Atlas, might be that kind of debris. Functional, durable. Not meant to survive forever, but long enough to be found. Science isn't meant to settle. Let's be clear. This isn't proof. It's a possibility. The moment we shout aliens is the moment science closes the door to better explanations. But the moment we refuse to ask what if it's not natural, it is the moment we fail science. Thrust without debris, spin without drift, energy without explosion, signal without voice. None of these proves intelligence, but all of them strain coincidence. And somewhere, between the silence of physics and the echo of function, it is a shape, one that doesn't quite belong. And if that shape is a gift, or a warning, or just a remnant, we won't know until the next one comes, and we're ready to look again without blinking. If you strip away the mystery, the speculation, the headlines about alien messengers or self-steering probes, what you're left with is motion pure, mechanical motion. And motion, in the silence of space, is never random. It is the language of physics. It is the fingerprint of origin. So when 3I, Atlas, began to rotate, scientists paid attention, because the way something spins tells you how it was born, how it's built, and sometimes, if you listen long enough, what it's hiding. Let's begin with the basics. 3I, Atlas, has a rotation period of about 8.3 hours. That's fast, but not extraordinary. Comets and small bodies in our own solar system spin at similar speeds. The surprise isn't in the speed, it's in the stability. Because from the moment we began observing it, its light curve, the periodic variation in brightness, as it rotated, was incredibly stable. That means the object wasn't tumbling, wasn't wobbling chaotically, like many interstellar or outer solar system bodies. It was holding itself together, spinning in a coherent, predictable way. That's odd. Most natural objects, especially comets, enter the inner solar system with irregular shapes, volatile jets, and sublimating surfaces that cause constant, erratic changes in spin. This is due to what's known as thermal torque, the force created when sunlight heats one part of a rotating object more than another. As material sublimates, usually gases like CO2 or H2O, the escaping molecules exert tiny forces on the body, slowly altering its spin rate and axis orientation over time. But 3I, Atlas, didn't show these signs. Its spin didn't accelerate. Its angular momentum, the fundamental property that describes how fast and in what direction it rotates, remained surprisingly stable. And the axis, it seemed locked. Now, axis lock isn't impossible, but in natural systems, it usually comes after long periods of energy dissipation. A comet, for instance, might evolve into a more stable rotation state after several passages near the Sun, losing volatile materials and slowly stabilizing. But 3I, Atlas, isn't from around here. It's not a periodic visitor, it's interstellar. This is its first and likely only passage through our solar system. So how does a first-time visitor arrive already balanced? One possibility is shape. The light curve amplitude suggests a moderately elongated body, not a perfect sphere, but not an extremely stretched rod either. This shape, combined with the correct spin axis orientation, could theoretically resist chaotic tumbling. But again, it's the stability over time that's perplexing. Remember, 3I, Atlas, is experiencing non-gravitational acceleration. We know jets are active. CO2 outgassing has been inferred from motion, if not directly imaged. That should be messing with the spin. And yet, over months of observation, no significant precession, the slow wobble of a rotating body's axis, has been detected. Precession is expected in almost any jetting body. It's what happens when thrust doesn't align perfectly with the spin axis. It's what makes comets wobble and their light curves shift. But here, we don't see that. Could the jets be aligned with the spin axis? That would be extremely lucky, or extremely intentional. If you engineer a body with venting mechanisms carefully aligned to its rotation, you can generate controlled thrust without introducing torque. This is basic physics, but difficult to achieve by accident. Nature doesn't tend to optimize thrust symmetry, it just vents where it can. Alternatively, perhaps the material distribution within 3I, Atlas, is uniform in a way that resists torque, but again, highly unusual. Most cometary bodies have chaotic internal structures, with voids, dust, and frozen gases interspersed unevenly. This leads us to the hypothesis that perhaps this isn't a comet at all, not in the traditional sense. Some have speculated it's a fragment of a larger body, broken off long ago and shaped by a different process, maybe even by internal collapse or extrusion, leading to a natural gyroscopic shape. But that theory struggles under scrutiny because it still requires an explanation for the non-evolving spin profile. The idea that it was born spinning and simply never destabilized doesn't align with the observable forces it's encountering. Which brings us to an even stranger possibility: axis lock through design. There are ways to build a rotating body so that it naturally resists precession gyroscopes, reaction wheels, damped mass centers. If 3I, Atlas, were engineered, its current behavior would make sense. But that's a heavy claim, one that science must approach with reluctance, not eagerness. So, we stay with the data. Meerkat confirmed the presence of water through the 18 cm OH emission line. That suggests active sublimation. And active sublimation means variable surface pressure, and variable surface pressure means torque unless it's countered, and it's not being countered by spin evolution. So, by what? Let's talk about thermal lag, the delay between peak solar input and peak outgassing. For natural bodies, this lag usually creates off-center thrust. But if 3I, Atlas, has subsurface chambers or vent conduits shaped to channel sublimation outward through very specific vectors, it could preserve both spin and direction of travel. That idea is extreme but not unphysical. We've designed similar things on Earth: spacecraft with attitude control via microthrusters, rotating satellites stabilized by internal mass distribution. Does that mean 3I, Atlas, is artificial? Not necessarily. It may be that the object's current spin behavior is a statistical outlier, a natural configuration that just happens to resist destabilization better than expected. But the spin profile remains a key signature because it's measurable, repeatable, and immune to interpretation bias. Light curves don't lie. Angular momentum doesn't bend to opinion. That's why spin matters. Because amid all the speculation, the jets, the tail, or lack thereof, the chemistry, the thermal survival spin, is physics. It's one of the few things we can actually measure directly from afar, and what we've seen isn't easy to explain away. so we keep watching. With every frame added to the timeline, with every rotation documented without shift, the silence grows louder. We're not claiming aliens, we're claiming a puzzle, a persistent one that spins in defiance of the random, in defiance of the chaotic, and maybe, just maybe, in defiance of chance. And in the vacuum of space, motion is memory. What 3i, Atlas remembers, is written in how it turns. In science, seeing is never believing. It's only the beginning of the doubt. Every image you've seen of 3i, Atlas, those luminous plumes, narrow jets, streaming arcs, feels like evidence. Something is thrusting, something is breaking out, something is there. But hold that thought, because the truth is, many of those features don't exist. Not out there, not in space. They exist in us. In the cameras, in the software, in the stacking, the interpolation, and the alignment algorithms we built to see clearer and sometimes end up seeing more than is actually there. Let's walk carefully through this illusion. When astronomers point their instruments at a fast-moving object like 3i, Atlas, they face a core problem: motion. The object is moving, but the stars are fixed, or rather, from Earth's viewpoint, the reverse is true. Either way, to capture a sharp image, you must choose what to lock onto. If you track the stars, the object smears. If you track the object, the stars smear. This choice, simple as it seems, sets the stage for layers of visual distortion. Now add exposure time. A single frame might last 30 seconds, 90 seconds, or even several minutes. In that time, cosmic rays strike the detector. Random thermal noise bleeds into the pixels. Light from nearby sources scatters, creating subtle gradients. And worst of all, faint signals begin to merge into shapes. But a single image is rarely enough. So we stack. Stacking is the process of aligning and averaging many frames to increase the signal-to-noise ratio. Done properly, it allows us to see what a single image would never reveal. Faint tails, subtle jets, the whisper of coma structure. Done poorly, it creates ghosts. Imagine a jet that isn't real, just a smear caused by imperfect alignment across 10 slightly shaky frames. Imagine a tail that points not away from the sun, but toward a noisy pixel cluster amplified by stacking. These are not science fiction, they're documented risks in astrophotography. And 3i, Atlas, being faint and fast, is particularly vulnerable. Some of the most circulated images of the object's tail show what appears to be a narrow, sun-facing jet, seemingly defying the expected anti-solar orientation. But these features often show up in images with long exposures and uncertain calibration. The jet sometimes appears in one frame but not the next. It shifts position slightly with the camera angle. It lacks spectral confirmation. In short, it could be an artifact. Let's be clear, this doesn't mean all visible structure is fake, but it does mean we must approach visual data with skepticism, especially when the implications are enormous. Extraordinary claims, like an interstellar object actively thrusting against its own trajectory, require extraordinary scrutiny. Even professional observatories are not immune to error bars. Different filters produce different apparent structures. Image processing pipelines apply various denoising and sharpening algorithms. One observatory's artifact can become another's confirmation. This is not dishonesty. It's the cost of looking deeply into the dark. The problem is compounded by public dissemination. When raw data becomes a colorized, high-contrast image on social media, the boundary between reality and interpretation blurs. A slight enhancement becomes a jet, a smudge becomes a signature, and the public, unfamiliar with the nuances of data reduction, sees certainty where only approximation exists. This isn't a flaw in curiosity, it's a flaw in confidence. We want to believe the sky is speaking clearly, but the sky, like the mind, is often full of projection. There's another layer: astrophotography bias. This refers to the tendency to see what you expect or want to see in the data. It's cognitive bias meeting cosmic noise. Once the idea of a sun-facing jet caught fire, observers began to look for it subconsciously, favoring interpretations that confirmed it. Alignment parameters were chosen accordingly. Contrast curves bent to reveal the hint of structure. And one hint, once shared, becomes a narrative. This is where science becomes fragile. Not because it's wrong, but because it's human. Take the case of the anti-tail. This is a real optical phenomenon, caused by the dust sheet geometry and viewing angle. To a human observer, it appears as a tail pointing toward the sun, a paradox, unless you understand the 3D spatial relationship involved. But how many observers know this? How many renderings are correct for it? And how many reposted images, simply as proof that the object is defying solar physics? This isn't just about 3I, Atlas. It's about the nature of observation itself. Every telescope is a translator. It converts photons into electrons, voltages into bits, and bits into beliefs. Between each layer, noise enters. And noise, if dressed carefully, becomes a story. We know this. It's why science uses error bars. It's why peer review exists. But in the age of viral space content, nuance is the first casualty. A tail looks real, and suddenly it is. And yet some features remain, persist across frames, appear in independent observations. How do we draw the line? Here is where humility matters. We must stop pretending every image is a window. It is a painting sometimes done in darkness, sometimes smeared by motion, sometimes touched by the artist's own hand. That doesn't make it worthless. It makes it incomplete. And that's what science is supposed to be, a discipline of working with the incomplete. So, what does this mean for 3I, Atlas? It means the jet may be real or not. It means the brightness variation may be due to rotation or noise. It means the lack of coma in stacked frames may be genuine, or a limit of the telescope's resolution, sky brightness, or processing pipeline. It means that a visual claim, no matter how compelling, must pass through the fire of spectroscopy, multi-wavelength confirmation, motion modeling, and, above all, repeatability. Because the most dangerous lies are not told, they are seen. The human brain is an image processor. It evolved to find faces in clouds, predators in shadows, patterns in static. It is very good at making meaning where none exists. And when the source of that image is a cosmic traveler, already cloaked in mystery, the temptation to believe what we see is overwhelming. But real science does not trust its eyes. It trusts its process. So, yes, look at the pictures, but hold them lightly. Ask what you're not seeing. Ask what was filtered out, cropped, saturated, or interpreted. Ask who processed the image, and how. Ask what instruments failed to confirm it. Because in the shadows of space, truth is often less visible, not more. And in the age of digital certainty, sometimes the only honest image is the one that says, "We don't know." That sentence, that moment of restraint, is where science truly lives. Not in the certainty of color-coded jets, but in the quiet admission that a smear of light across a sensor might be a whisper from another world, or just a glitch in our lens. And the only way to know is to keep looking, not for what we hope to see, but for what the sky actually shows when all the layers of interpretation are stripped away. Only then, maybe, will we understand what it means to truly observe. There is a kind of silence that speaks louder than sound. In science, we are trained to listen to instruments, to numbers, to the faintest hum of the universe's machinery. But what happens when there is no hum, when the sky, so full of motion, offers not a whisper? This is the paradox of 3I, Atlas. We have tracked its trajectory, we have plotted its spin, we have measured its brightness, its geometry, its mass loss, and its thermal endurance. But through it all, one thing has remained strikingly consistent. It hasn't spoken. No unexpected radio burst, no exotic frequency, no anomalous modulation. The object is active, visibly ejecting gas and showing signs of thrust, but not communicative, not in any way we recognize. And that, oddly enough, may be the most unsettling thing about it. To be clear, this silence is not a blank slate. It is a known silence charted through arrays like Meerkat and facilities scanning at a wide range of wavelengths, particularly in the radio. We know what absence looks like, and in this case, absence appears quite distinct. From the moment of its perihelion approach, many had hoped for something more, a data point that didn't fit, a spike in a band that defied classification, a blip that might require a footnote or a theory. After all, when interstellar objects like Oumuamua came through, the silence felt like a disappointment. This time, people were ready. But the silence persisted. The 18 cm OH line, confirming water presence, was the only notable feature. Beyond that, nothing. No structured signal, no narrowband repetition, no Morse-like pattern in the noise floor. The kind of anomalies we chase for SETI, the anomalies we sometimes hope to see, were nowhere to be found. At first glance, this seems like a relief. If the object were transmitting or resonating unnaturally, the implications would be enormous and controversial. But deeper down, this stillness is not comforting. It feels intentional, or worse, indifferent. Here is the subtle question scientists are asking, even if they don't phrase it aloud. What if this silence isn't meaningless? What if silence itself, when expected anomalies are missing, is the anomaly? Let's unpack that. In a universe teeming with background radiation, electromagnetic interference, cosmic rays, plasma bursts, and errant emissions, it's normal for things to be noisy. Even comets, especially active ones, sometimes emit in ways we don't expect. Charged particle interactions, solar wind reactions, and molecular chemistry can all create brief emissions that show up on our scopes. But 3i, Atlas, has been remarkably quiet across those dimensions. Could it be an observational gap? Certainly, that's possible. Many radio observatories don't have continuous coverage. Our instruments sweep, pause, return. They miss windows. They are bound by scheduling, atmospheric conditions, and funding constraints. A signal that fires for 5 minutes on a Tuesday afternoon when no one was watching could easily be missed. And with an object as fast and unique as this, timing matters. So part of the silence could be ours. A silence of circumstance, of limitation. But then there's the other side. What if it was always quiet? Always meant to be, not by intent, necessarily, but by nature? That brings us into philosophical territory. When we look at something behaving strangely, moving with non-gravitational acceleration, surviving heat it shouldn't, breaking energy models, and then find nothing else, it forces us to confront a bias. We expect the unknown to be noisy. We expect the mysterious to declare itself through anomalies, not through restraint. This is a mirror to human psychology. We think the significance must be dramatic. We look for the loud, the bright, the signal in the static. But some of the most important things in the cosmos arrive in whispers or in silence. Black holes do not glow. Neutrinos pass through us by the trillions, unannounced. Dark matter refuses to interact, even as it shapes galaxies. And now, maybe, this visitor from another star system passes through our own, altering models, challenging theories, but never once speaking in a way we expected. What does that mean? Some have speculated that a lack of artificial signals could still be a type of signal. The logic goes like this. If an object were advanced enough to design its own propulsion, stability, and geometry to resist sublimation and align itself for energy efficiency, might it also know how not to be seen? The principle is called communication minimization. In systems theory, especially for stealthy or efficient probes, silence is often the ideal state. Emissions cost energy. Emissions draw attention. Emissions create a profile. A well-designed object, sent to observe or measure, might be designed not to emit unless necessary. This is, of course, speculative, but it introduces a provocative layer. Could the absence of noise be part of the design? On the other hand, we must hold fast to scientific humility. There are plenty of natural reasons why 3i, Atlas, might be quiet. Its volatile content may be limited to H2O and CO2, producing only standard emissions. Its structure may suppress radio reflection. Its axis orientation may shield us from brief events, or perhaps we're simply not tuned to the right channel. We assume communication would come in a way we understand: modulated radio, pulsed light, repeating mathematical patterns. But what if that assumption is wrong? What if the noise we're missing is in a spectrum we've never considered, or worse, in a mode we cannot perceive? The problem with silence is that it's hard to test. Absence does not prove absence, but it forces us to reframe how we interpret presence. A quiet object isn't necessarily boring. It may, in fact, be more advanced, more refined, more resolved, or simply more foreign. And in this lies the heart of the philosophical shift. We want the universe to speak to us, but sometimes it teaches by not speaking. It invites us to observe without reply, to measure without feedback, to ask better questions, not louder ones. In the case of 3i, Atlas, the silence invites a strange new discipline, restraint, to look at an object that baffles and still say, "We don't know," to publish data without drama, to chase follow-up observations without assumptions, to accept that not every mystery explodes into revelation. Sometimes the story is the absence of a story, and in that absence, meaning waits. A silent object moving with intent, if that's what this is, challenges more than physics. It challenges our expectation that everything unknown will arrive with fireworks, that every anomaly will scream its truth, that every cosmic question will be answered in HD, with clear captions. But maybe some visitors don't come to explain. Maybe they will come to pass. But sometimes it teaches by not speaking. It invites us to observe without reply, to measure without feedback, to ask better questions, not louder ones. In the case of 3I, Atlas, the silence invites a strange new discipline. Restraint, to look at an object that baffles and still say, "We don't know." To publish data without drama. To chase follow-up observations without assumptions. To accept that not every mystery explodes into revelation. Sometimes the story is the absence of a story, and in that absence, meaning waits. A silent object moving with intent, if that's what this is, challenges more than physics. It challenges our expectation that everything unknown will arrive with fireworks, that every anomaly will scream its truth, that every cosmic question will be answered in HD, with clear captions. But maybe some visitors don't come to explain. Maybe they will come to pass. But something stranger. Start here. The architecture of our detection systems. We listen in bands. We filter for signals with known characteristics. Modulation, pulse timing, polarization. If it doesn't fit the profile, we filter it out. Our ears are tuned to what we know how to recognize. But if 3I, Atlas, was transmitting with a purpose beyond us or before us, what if it never intended to use our bands? Think about the range of possibilities. Quantum communication isn't science fiction anymore. Lab tests have shown entangled particles transmitting changes in state over vast distances. No classical signal, no delay, no radiation spike, just a quiet shift. If an advanced technology chose quantum channels, it would not light up our dishes. It would leave no EM signature. It would look like nothing. Exactly what we see. But there are other candidates too, some only emerging in the physics literature. Dark photons, a proposed cousin of regular photons, part of the hypothetical dark sector. They don't interact with regular matter in the same way, but in certain models, they can oscillate into normal photons under specific conditions. If a signal were encoded in this medium, it wouldn't just be hard to detect. It would be undetectable unless you built a receiver tuned to a physics we don't yet use. If that sounds like speculation, it is. But speculation guided by theory. And theory is where science begins. What if the signal isn't in what's emitted, but in what's avoided? EM masking is a known technique in military stealth. You don't just stop sending, you send just enough to blend into the noise. A decoy signature, a thermal profile mimicking the environment, a radio pulse that looks like a glitch. If 3I, Atlas, wanted to remain hidden or simply uninterpreted, it could be broadcasting on purpose, in a way that looks unintentional. A mask, not a message. And what of signal compression? We compress information every day, text, image, sound, into smaller, more efficient formats. A species with a deep mastery of signal theory might encode vast volumes of information in something that looks like a noise floor to us. A blink, a fluctuation in polarization, a subharmonic barely above the system noise. The message could be there, hiding in plain sight, but requiring a decoder we don't possess, not just a machine, but a paradigm. We're reminded here of the WOW signal, a single, narrowband radio spike in 1977, never repeated, never explained. Was it a test? A transmission that required a response we never gave? What if 3I, Atlas, is sending a similar kind of moment, a one-shot signature, not meant to repeat, but to probe, not for contact, but for context? There's also the time domain to consider. Most of our surveys look for steady-state sources or brief bursts. But what if the signal is episodic, or embedded in orbital timing, or waiting for solar alignment to bounce? Imagine a signal that only activates when the object is in precise geometric relation to the Sun, Earth, and another body. A kind of cosmic triangulation key. We may have missed the moment, or not yet reached it. Then there's a darker question. What if it's not sending for us? Communication, as we understand it, presumes a recipient, but a probe, or a remnant, or a beacon may be transmitting regardless of who's listening. Think of a black box on a crashed airplane. It records, it pings, not because someone is there to hear, but because the act of sending is part of the system. If 3I Atlas is a remnant, something broken, drifting, once sent and now alone, it may be broadcasting endlessly. But to no one, or to someone not here yet, this brings us to the purpose. Why would something transmit at all? To announce? To navigate? To seed? To test? To trigger? Each possibility opens a different doorway. A navigational beacon would prioritize precision over power. A seeding signal might piggyback on local chemistry using OH or CO2 as modulation media. A test might wait for interaction, a laser bounce, a radar ping, a spectral scan, and only then respond. And a trigger? That's the most unsettling. Something that activates only when conditions are met. Mass, energy, curiosity. Something that waits. Let's stay grounded. There is no evidence, none, that 3I Atlas is sending a message. But there is also no evidence that it isn't. What we have is a hole, a space in our data, a set of assumptions that may not apply. And that, in science, is the beginning of every great shift. The map ends, the questions begin. Avi Loeb, ever the provocateur, has suggested that non-gravitational motion, particularly in objects like Oumuamua and 3I Atlas, shouldn't be hand-waved away. That anomalies deserve explanation, not dismissal. His Galileo project is built on that premise. Look again, ask again, build better eyes. That spirit, skeptical, careful, brave, is what guides this thought. If 3I Atlas is transmitting something else, then our job isn't to declare no signal. It's to ask, what are we missing? What haven't we built? What frequencies haven't we scanned? What theories haven't we dared to test? Because the sky is full of silence, and sometimes silence is the loudest thing we hear. Science is often presented as emotionless. Charts, equations, peer-reviewed journals. But that's never the whole story. Behind every paper is a person. Behind every data set, a decade of study. And behind every silence, especially one as strange as 3I Atlas, there is the murmur of a scientific community both intrigued and uncertain. Because 3I Atlas didn't just bend physics, it bent the people studying it. Reactions have ranged across a spectrum: curiosity, skepticism, restraint, quiet fascination, even professional fear. And while no major institution has formally declared it anomalous, few have dismissed it either. That middle ground, that murky zone between maybe and don't say it out loud, is where most astronomers now find themselves. Let's start with the cautious ones. Many researchers who worked on Oort cloud models or comet morphology expected strange things from interstellar visitors. So, when 3I Atlas began displaying signs of non-gravitational acceleration, most shrugged at first. Comets do that. Sublimation pushes them slightly off course. It's standard textbook stuff. But over time, as data from telescopes like Meerkat, Vera Rubin, and others piled up, that shrug grew stiffer. "This one doesn't behave," said one planetary scientist at a recent conference off the record. "The direction is too stable. The acceleration curve is too clean. If it's outgassing like it read the manual for controlled propulsion." Others focused on the spin. "Any object rotating should show jet precession unless there's some locking mechanism," noted a dynamicist from the University of Michigan. "But we don't see precision. It's like the jets know where to point. That's not normal." But caution in words doesn't mean absence of doubt. In private Slack groups, astronomy discords, and late-night Zoom calls, a different tone emerges. "I don't want to say it," one astrophysicist wrote, "but this is what we thought we'd see if we ever saw. Something engineered." Of course, few have been as publicly willing to voice that possibility as Avi Loeb. Loeb, the former chair of Harvard's astronomy department, has long been a lightning rod. When Oumuamua passed through in 2017, he famously published a paper suggesting it might be artificial. Since then, he's doubled down, founding the Galileo project, pushing for data transparency, and calling out what he terms scientific cowardice. To dismiss anomalies because they make us uncomfortable is to betray the essence of science, Loeb said during an interview. 3I Atlas deserves scrutiny, not silence. But that kind of courage or provocation, depending on your perspective, comes at a cost. Many in the field distance themselves from Loeb, not necessarily because they think he's wrong, but because they fear association. Peer pressure in science is real. Careers are built on reputations. One too bold claim can cost a grant, a paper, a promotion. Tenure doesn't mean immunity, one postdoc said. It just means you get judged in quieter rooms. And then there are the observers, those who don't speak out but don't look away either. At the Vera Rubin Observatory, which has been silently compiling massive sky datasets, several team members have reportedly flagged 3I, Atlas's motion, as non-compliant with known models. Yet no formal statement has been made. The data is public. The patterns are there. But the framing remains neutral. We publish observations, one researcher clarified. Interpretation is someone else's job. Jason Wright, a respected astronomer at Penn State known for his careful work on technosignatures, has walked a tightrope of reason. We have to be very clear about what we do and don't see, he wrote in a recent blog post. Yes, 3I, Atlas, shows non-gravitational acceleration. Yes, that could be due to outgassing, but we lack direct imaging of a coma. And yes, we should be open to the full spectrum of explanations, but that does not mean leaping to conclusions. That kind of intellectual honesty is rare and vital, but it's not without tension. Many astronomers admit, behind closed doors, that the cultural climate of the field discourages curiosity when it crosses certain boundaries. There are soft taboos, said one spectroscopist. Well, theorize about dark matter decay before we publicly consider a spacecraft. This isn't because of arrogance. It's because science, especially astronomy, has been burned before. The history books are filled with embarrassing claims, canals on Mars, alien radio bursts, even face-shaped rocks. Each time, the community paid a price in credibility. We don't want to be the next face on Mars, a cosmochemist explained. Yet something is shifting. Younger astronomers, less tethered to legacy thinking, are beginning to whisper more openly. In forums and peer-to-peer circles, the conversation is evolving. What if 3I, Atlas, is the first object we've seen that hints at a signal not in the data, but in the design? One PhD candidate mused. What they mean is this. What if the strangeness isn't noise but function? It's not a widely accepted idea, but it's not laughed out of the room either. That change in tone, subtle, slow, is itself a kind of signal, because even without consensus, even without declarations, the community is reacting. Telescope time is being quietly shifted, models are being adjusted, papers are being drafted with phrases like unexplained behavior and possible non-standard mechanisms. And behind every one of those phrases is a person, a scientist, reckoning with something they can't quite explain, but also can't ignore. This is the human side of science. The cautious reviewer who flags a bold paragraph for revision, not because it's wrong, but because it might be right too early. The early career researcher who asks the weird question only after the Zoom call ends. The quiet engineer who reruns the tracking data, not once, but 7 times just to be sure. And the senior professor who, in a lecture hall, says, I don't know, but I'd like to find out. 3I. Atlas didn't just enter our solar system. It entered our discourse. It entered the fragile, beautiful balance between belief and doubt that defines real science. And maybe that's the most powerful thing it's done. Not to prove, not to speak, but to make us wonder and wrestle with what we think we know. Because at the end of every equation, there's always a person asking, what if we're missing something? We look to the sky for answers. Always have. Always will. But sometimes, what the sky sends back isn't a message written in light or orbit or dust. Sometimes, it's a mirror and 3I. Atlas, this silent, accelerating, unbroken traveler, may be the clearest mirror we've seen in years. Because for all the energy we've spent trying to decode its movement, measure its water vapor, or simulate its thermal stress, there is a deeper current flowing beneath it all, one that says more about us than it does about the object. Let's start with a simple truth. Humans are not objective creatures. We pride ourselves on reason, on empirical observation, on the scientific method, but we filter every piece of data through a perceptual lens shaped by bias, fear, tradition, and the desire to belong. And when an object like 3I, Atlas, enters our solar system, defying a dozen assumptions in a single glide, it doesn't just challenge our models. It challenges our identities as scientists, thinkers, and observers of the universe. From the start, 3I, Atlas, felt wrong. It didn't come from the usual direction behind or above. It wasn't dirty enough, wasn't unstable enough, didn't fragment on cue like a proper interstellar rock. It accelerated where it shouldn't, spun with coherence when chaos was expected, and displayed jet behavior that refused to precess. At every turn, it refused to conform to our mental category of comet. And what did we do? We hesitated. We looked for a coma that wasn't there. We waited for tail behavior that never appeared. We cited uncertainties, margin of error, and inconclusive mechanisms. Not because the data was bad, but because the implications were worse. Because what if it's not a comet? What if the models we trust are incomplete? Or worse, wrong? The discomfort wasn't in the object, it was in ourselves. It turns out, the real test, 3I, Atlas, presents, is not to physics, but to psychology. Are we able to hold contradictory possibilities in mind without collapsing into panic or ridicule? Can we look at an anomaly and say, this breaks the pattern? Let's re-examine the pattern, instead of forcing the anomaly to wear a mask we're more comfortable with. Do we possess the humility to admit when our frameworks, our instincts, even our instruments, might be blind? This isn't just academic. There is a name for the internal pressure we feel when reality contradicts our assumptions. Cognitive dissonance. And 3I, Atlas, in its quiet glide, has become a dissonance generator. Take, for example, the standard sublimation model for non-gravitational acceleration. It works beautifully on most comets, but when 3I, Atlas, began accelerating in ways too smooth, too persistent, and too precisely aligned to its spin axis, the community clung harder to the model, not looser. Some even proposed CO2 jetting from subsurface layers, with no coma, no tail, no rotational precession, and expected the rest of us to accept that as standard. But it wasn't standard. It was a patch, a workaround to protect the comfort of the model, not the clarity of the data. Why? Because changing a model means more than rewriting equations. It means reopening textbooks. It means challenging reputations. It means funding new instruments, defending controversial proposals, and risking ridicule from peers who would rather be wrong in consensus than correct in isolation. That's the real force 3I Atlas is exposing. Not thrust, not heat, not molecular decay, but inertia. The inertia of thought. And yet, this moment holds potential. Because cracks, when seen clearly, are where light gets in. We've been here before. There was a time when the idea of an Earth not at the center of the universe was heresy. When Galileo looked through his telescope and dared to say, this moves, not that. He wasn't just arguing astronomy. He was threatening a worldview. And the response wasn't a scientific debate. It was suppression. Today, we like to think we're past that. But are we? When a respected academic like Avi Loeb suggests the possibility of artificial origin, not declaration, not certainty, but possibility, he is met with ridicule more often than rebuttal, not because his math is wrong, but because his questions are unwelcome. That's not science. That's fear. And fear is a terrible compass. So maybe 3I, Atlas isn't here to reveal new laws of motion. Maybe it's here to reveal how we respond when laws begin to fail. We like our anomalies to be temporary. Glitches, something we can correct with better measurements or a revised coefficient. But what happens when the anomaly persists? What happens when the object doesn't explode at perihelion, doesn't fragment, doesn't lose cohesion despite impossible heating curves? What happens when the silence in the radio bands isn't an absence, but intentional? What happens when the data keeps pointing to a question we're too afraid to ask? We either break or we grow, and growth begins with humility. Humility doesn't mean surrendering rigor. It doesn't mean anything goes, or giving equal weight to every wild idea. It means acknowledging that we don't see the universe as it is, we see it as we are. Through models, through metaphors, through paradigms built on generations of inherited certainty. 3I, Atlas has become a paradox, a foreign object that is now the most intimate test of who we are as observers. It asks nothing of us. It doesn't glow with messages. It doesn't pivot to match our interest. It just moves on a trajectory we didn't predict, with behavior we can't fully explain. It's not screaming. But maybe that's the point. maybe the quietest anomalies ask the loudest questions. And those questions aren't about propulsion, or shape, or composition. They're about perception. What are we willing to see? What are we unwilling to let go of? What stories do we force on data, just to preserve the illusion that we understand? Because if 3I, Atlas, had arrived in 1700, it would have been a divine omen. In 1900, a new kind of comet was discovered. In 2000, perhaps a curiosity. But here, in 2025, with all our instruments, algorithms, and spacefaring dreams, it is a mirror. And in that mirror we must ask, is our greatest obstacle the object or the lens? There's a truth in astronomy that many forget. The sky never rests. It does not finish its revelations with a single event, nor does it pause for our understanding to catch up. What begins with one strange object seldom ends there. 3I, Atlas, may be the loudest whisper we've heard in years, but it won't be the last. Somewhere beyond Neptune's slow dance and the edge of the Kuiper belt, another visitor is already en route. Faint, unnamed, undetected for now, but inevitable. Not because we've cracked some cosmic code, but because the sky has always delivered the next enigma. It is a system built on motion, and everything in motion must eventually arrive. This isn't speculation, it's statistics. The more we look, the more we find. And with the advent of new sky scanning systems like the Vera Rubin Observatory, we are entering a new phase in our relationship with space. One defined not by luck, but by vigilance. Before 1I, Oumuamua, interstellar objects were theoretical. After 2I, Borisov, they became expected. Now, with 3I, Atlas, the unexpected is becoming routine. These aren't isolated anomalies. They are the beginnings of a pattern we are just now beginning to recognize. Let's speak practically. The Rubin Observatory, set to become fully operational soon, will scan the southern sky every few nights with unprecedented depth. It will catch objects that once slipped between the cracks, those too faint, too fast, or too oddly angled to be noticed by legacy systems. Instead of hearing about new visitors from one observatory scrambling for telescope time, well, get alerts in near real time, shared across networks and continents within minutes. Imagine this, a detection pipeline that doesn't just notice anomalies, but anticipates them. A system where image differencing, motion detection, and orbit modeling are automated and refined with every new observation. With Rubin's 3.2 gigapixel camera and 10-year legacy survey of space and time, LSST, we won't just see more, we'll see faster, earlier, and more clearly. This changes everything, because now, when the next visitor begins its inbound trajectory, we won't be relying on a single astronomer's luck or one survey's margin. We'll be operating with a planetary nervous system, one where every data point is cross-checked, where uncertainties shrink not over weeks but over hours. Well, catch the inbound slope, the light curve from afar, and the spin modulation before it enters our blind spots. Well, be ready, or at least more ready than we were. And this readiness matters, because each new visitor carries the possibility of rewriting what we thought was settled. With Oumuamua, we learned interstellar objects could be small, fast, and thin. With Borisov, we saw CO-rich chemistry that shattered our assumptions about what comet-like even means. And with 3I, Atlas, we are being asked to consider not just what an object does, but what we assume when it does something unexpected. What happens when the next object does all that, and more? What if it outgasses in strange molecules? What if it fragments and reforms? What if its albedo matches no known material? Or if it arrives not alone, but in formation? These are no longer the questions of science fiction. They are preparatory hypotheses for an age where discovery happens on the edge of comprehension. The point here is not to sensationalize the next object. The point is to understand that the rhythm of discovery has accelerated. The sky has become more transparent, and we, thanks to Rubin, NEO Surveyor, JWST, and the new Lagrange point sentinel concepts, are finally poised to listen well. This new readiness comes with responsibilities, not just technical, but philosophical. Are we prepared to treat the next anomaly with openness, not reflex? Will we allow science to be surprised? Or will we again try to flatten the strange into the familiar, just to avoid the discomfort of change? Because 3I, Atlas, showed us the cost of hesitation. The delay between observation and open-minded analysis. The weeks wasted waiting for confirmation of normal behavior that never came. The emotional inertia resisted the full implications of what was right in front of us. Next time, we must move faster, not in panic, but in curiosity. Preparedness isn't just about hardware, it's about mindset, and the next visitor will test both. Already, some systems are adapting. The International Astronomical Union's Minor Planet Center now receives real-time updates from surveys across the globe. AI models are being trained to distinguish between asteroids, comets, and anomalous objects within hours of detection. Amateur astronomers are becoming vital nodes in this new network, capable of confirming trajectories, observing light curves, and flagging unusual behavior faster than large observatories burdened by scheduling. We are decentralizing discovery, and this decentralization mirrors a larger truth. The next cosmic lesson won't be delivered in a press release. It will be caught in the blur of motion across 16-second exposures, in the rise and fall of brightness across days, in the silence between expected emissions. We will have to pay attention not just to the object, but to the gaps, to the absences, to the moments when the data defies compression into old labels. So, when another one comes, and it will come, we must ask, will we recognize it early enough? Will we observe with enough nuance? Will we question quickly enough the assumptions it breaks? Or will we again resist its message in favor of comfort? The future of astronomy isn't just about seeing deeper, it's about thinking differently, because every new object is a potential paradigm crack, a small fissure in our understanding that could widen into revelation if we let it. 3I, Atlas, is not the final mystery. It is the preface. The next chapter is already inbound. We may not know its name, we may not know its shape, its chemistry, or its trajectory, but we know it's coming, and this time we won't just watch, well listen, well test, well remember what happened when we didn't move fast enough, didn't ask boldly enough, didn't let the data speak louder than the doubt. Another one is coming. Let's be ready to meet it with eyes open, tools sharp, and minds wide. Because in the expanding silence between stars, each visitor carries not just a mystery, but a chance to grow. What if the goal was never to decode, but to feel? What if the silence in the data wasn't an absence, but an offering? Somewhere along the way, science became synonymous with answers. Measure, model, predict, confirm, publish, repeat. But the story of 3I, Atlas, doesn't want to be resolved. It resists the easy headline. It dodges every therefore. It doesn't ask us to conquer it. It asks us to notice. The object came and went, yes, but it left a shape in our minds, a negative space of knowing, a contour of mystery, lit only by the questions it refused to answer. And maybe that's the point. Because in a universe this vast, with 100 billion galaxies and 10 to the power of 24 stars, perhaps the rarest thing isn't an anomaly, but the moment when we stop needing resolution. Wonder is not passive. It is not naive. Wonder is what remains when arrogance burns off. It's what happens when we realize our instruments are perfect and still insufficient. When every pixel is clean, every signal is confirmed, and we still whisper, but what is it? This, in the end, may be 3I, Atlas's most profound gift. Not the OH line at 18 centimeters, not the anti-tail geometry, not the non-gravitational acceleration, but the quiet permission to stand in front of a fact and feel awe instead of control. We have built entire civilizations on the pursuit of certainty. But certainty is not the same as meaning. Meaning lives in the echo, in the tension between data and interpretation, in the flicker between explanation and experience. You cannot plot awe on a light curve. You cannot compress mystery into a table of elements. You cannot catalogue the moment your breath catches, and yet those moments shape us. We remember not the math, but the feeling of the eclipse. Not the particle, but the silence after the nova. Not the object's classification, but the shape it left in our understanding. Science, at its best, is not the death of mystery, it is the amplifier of it. And so we return to 3I, Atlas, this quiet object that moved too fast and too strangely to explain. It had no bright coma, no wild tail, no photogenic outburst. It shimmered, it shifted, it whispered, and then it was gone. And maybe we missed nothing. Maybe this was exactly what the universe wanted us to see. that even in our most advanced moment, with supercomputers, space telescopes, and quantum theory, we can still be brought to our knees by a piece of ice. Is that not beautiful? We mapped its trajectory across the sky, yes, but did we map what it revealed inside us? It showed us how we crave pattern, and how disoriented we become when the pattern dissolves. It showed us how quickly we split, some reaching for reason, others for poetry. And it showed us, perhaps above all, that we are still capable of wonder. Still, even now, even after all the equations, even after centuries of celestial mastery, even after we convinced ourselves that the sky had no more surprises, we were wrong, and being wrong, we felt alive. There is something sacred in that, because, for all our ambition, perhaps the true purpose of looking up was never to solve but to reconnect, not to dominate the unknown, but to remember we are part of it, not to fix the silence, but to sit beside it, not to light every corner, but to walk slowly in the half-glow. The sky is not an archive to be conquered, it is a mirror, and 3i. Atlas? It held it steady. So now, what do? We breathe. We listen better. We ask less for answers and more for presence. We remember that the universe does not owe us narrative structure. It offers movement, shadow, echo, and it invites us not to explain it all, but to walk with it anyway. We can let go of needing every line to close. We can live inside the ellipse. We can finally understand that perhaps we are not here to know the universe. We are here to be known by it, through the flickers we don't understand, through the signals that arrive with no key, through the light that touches us before we recognize the source. This is not romanticism. It's reality, because the science itself now tells us, the more we understand, the more unknowns unfold. Dark matter, dark energy, quantum weirdness. These are not gaps to be filled, they are invitations. To be humble, to be porous, to be amazed, to say, I see the data, and I still don't know, but I feel something. And that, too, is science. We are human not because we solve, but because we stand in wonder. And sometimes, the most radical thing we can do as scientists, as thinkers, as observers of this vast and beautiful chaos, it is to let the object pass, let the echo linger, let the breath deepen, and let the heart say, this too was enough. Let it be. Let it glow. Let it go.